So I work at the National Oceanography Center in Southampton, which some of you may know. But for some of you, and I realize I'm speaking to a very sort of mixed community here. So for those who don't know, the National Oceanography Center is the main center for marine science in the UK, has around 650 staff across 2 sites in Southampton and Liverpool. It's got a long history for ocean science, over 60 years in operation. Recently, in 2019, NOC became an independent organization with charitable status. We were previously owned by NERC, UKRI, and we are now an independent self-governing organization. So with all the changes that this implied. So NOC's mission is to make sense of changing seas, and that's a little bit the theme of my talk today, is all the changes that we see in the oceans and how Earth observation is contributing to understanding what's going on, or in this particular instance, perhaps not doing quite as much as it should. There are 3 pillars to what NOC is doing: is to undertake world-class science and technology development, to provide large research facilities and access to data, and to create value and public benefit by essentially providing the scientific evidence to support development of, for example, public policy. We also have a role in education and training, and we have some 60 or so PhD students that we supervise together with our co-located universities of Southampton and Liverpool, respectively, and also involved in several doctoral training programs and centers for doctoral training. And I mention this because the skill shortage that we talk so much about in space is also very much an issue for us in the ocean science world. And then a few words about me. I've actually updated my slides. It's actually 30 plus years, no longer 25 years, but 30 plus years experience in satellite Earth observation. It doesn't quite match the 44 years of the previous speaker, but certainly getting there. It really just underlines how these are sort of very long time span in Earth observation, or indeed in space, that is needed to take to make progress in some instances. So my specialism is in microwave remote sensing specifically, and I'm a marine physicist by background. So my interest is more in the physical aspects like currents and winds and waves, sea level, salinity, etc. And one of my more recent activities have been to be involved in proposing new satellite missions to address some of the gaps that we have in the ocean observing systems. So, for example, I'm involved in the New Space Scout Hydro GNSS mission, or GNSS reflectometry for winds, which I will not talk about too much today, simply because of time. And my more recent exploits have been with ESA Earth Explorers, where I was leading the SeaStar mission concept for currents and winds. But unfortunately, that has been rejected again for the 3rd time. And just because of the festive spirit, I decided that I will not talk about this, mainly because I may have to say some rude things by ESA, and I do not really wish to do this in public. But please come and talk to me at the cocktail party later, and I can tell you all about it. So I like to start my talks about just to remind people why the ocean is so important. The ocean is central to life on Earth. It's easily forgotten because we do not live in the ocean, but nevertheless, this is the front page here on the left from the Times magazine in September that actually mentions this makes the ocean the most important place on Earth. There are many reasons why this is the case. Of course, 71% of the Earth is covered by the ocean. It contains 97% of all water on Earth. It still baffles me that people can look at the water cycle without considering the ocean, but there we are. 50% of all the oxygen on Earth is produced by the ocean. It contains 95% of the Earth biosphere and is a primary source of protein for over 3 billion people. The United Nations have identified the ocean as the world's greatest ally against climate change, for the simple reason that the ocean has absorbed 90% of the excess heat from climate change, and has absorbed between 30 and 40% of CO2 fossil fuel emissions. So it is a pretty big hitter when it comes to the Earth system. The ocean is under pressure from global warming and human activities, and this is a non-exhaustive list on the right of all the kind of pressures and that result from global warming, such as accelerated sea level rise, sea ice decline, increased storminess, increased stratification of the ocean, which means that it's not overturning so much, which generates marine heat waves, etc. And then on the right, we have a non-exhaustive list of pressure from human activities linked to population growth, overfishing, dredging, agricultural runoff from land and into the ocean, etc., etc. So the United Nations has declared this the decade of the ocean for ocean science and sustainable development. And this has spurred a vast number of actions and programs worldwide that take a particular view on the ocean and what we need in order to make progress. And there's a notable focus in these actions on coastal predictions and on the use of more advanced digital technology like digital twins, for example, DITO, that some of you may have heard of. It is also mentioned at COP28, which has already been mentioned this morning. And only a few days ago, the Ocean Pavilion, which is a gathering of ocean ocean science organization worldwide, have come together to make a declaration about the ocean, really urging world governments to take urgent action to make sure that ocean science is supported to provide and support climate solutions. We have seen in 2023 record-breaking ocean changes. The ocean is in the news almost daily these days, and scientists need more data to understand the implications. And COP28 is hopefully going to be this vital change from what has been happening until now. If you want to see the full declaration, you can see the link there, or you can simply Google it if you like. So on the right, this is the kind of sum total of the in situ observations that we have. So when you look at it globally, it looks actually quite well populated. But when you try to zoom in, you can see on the right, you see that the amount of data we have from in situ sources is really small and makes it very difficult to support local decision making. It is at the local scales that we make decisions about investments, for example, about coastal protections and so on. And clearly in situ infrastructure by itself is not sufficient to do this. So this is where satellites come into play, and we get these beautiful images here. This is an optical image, an ocean color image over the Bordeaux area, just on the coast of France, showing these incredible sort of patterns of sediments, essentially the sediment plume out of the Gironde River, and these wonderful patterns that you see there, which are linked to a mixture of sediment transport, primary production, so for example, algae, pollution, river discharge, a whole mixture of things enabled by the action of currents, winds, and waves. And you can see here, even in these optical images, you can see these sort of patterns of wind and waves and those very, very small scale variability that you see there that is affecting the transport of material from land into the ocean. Now, this is an ocean color image, and we are very lucky to have it because it was a day without clouds. But more typically, over 80% of the planet is covered by clouds. So these images are relatively rare. Clearly, this type of information, this type of images contain a huge amount of information relevant, for example, water quality, and is relevant to a whole range of societal questions linked to fisheries, agriculture, coastal conservation, biodiversity, etc. All of these are under great pressure at the moment. But in order to interpret these images from ocean color, you cannot just assume that these patterns represent the current or displacement of water. So at the moment, you may be surprised to know that the information we need to make progress with this is linked to currents, winds, and waves, which is what I was proposing to do with CSTAR. But unfortunately, that wasn't enough to convince ESA on this instance. But nevertheless, there remains a critical need for information about currents, winds, and waves. And I hope people are as shocked as I am to think that in the 21st century, we still do not know how the ocean moves on our doorstep. Okay, moving on. So recently we did have a breakthrough in ocean technology through the launch of the Surface Water and Ocean Topography, SWOT. So for those who do not know, this is a bilateral or multilateral between NASA, so between the US, France, Canada, and UK. And this is an incredibly innovative technology which uses a cross-track interferometry for those who want to know. And you have this very long boom, kind of a cross-track that gives you SAR images with a slight sort of phase difference. That gives you images of surface water levels. So you get images of water levels, which is unprecedented. Until now, we've been measuring water levels along narrow tracks with our nadir pointing altimeters, but we've never seen the 2D surface expression of water levels. So the little movie on the side here is taken in the Atlantic. And what we see is this is taken at the crossover, and every image is taken 1 day apart. It was a very rare occasion when the satellite mission was taking measurement in the same place every day. And this big blue blob that you see moving across is a big eddy. So it's 100 kilometers so across, and it is of significant amplitude. This type of feature will have signatures in currents of the orders of meters per second. So very, very strong signatures. And we can see how quickly these features are propagating. And not only that, we see a lot of stuff happening around it at small scales as well. This is the first time we have actually seen this. Again, this is quite shocking to think that this is the first time we see how the ocean moves at the 1 day scale. The SWOT, we have a small project called SWOT UK that looks at the data from this mission in the coastal zone. Oh, the movie's moving, that's miraculous. So again, we have this validation project in the Bristol Channel where we happen to have overpasses from SWOT every day for 90 days during the Cal-Val phase. This is the only place in the world where we actually could look at an estuary with SWOT, because the number of places where SWOT was actually measuring every day was actually quite limited. We only had 15 orbits per day, as you probably know. But what this shows is that for the first time, we have images of water level in the coastal zone here, against which we can test our models. First time we are able to do this. Until now, you see those little red circles around the coast. These are our tide gauges. And normally, this is the information we have to try to understand what is happening across. And you can see how the water level changes both across the channel and along the channel, and in very different ways, depending on the stage of the tide. And the models are, well, they are in need of further improvement. So coming back to what is Earth observation doing for oceanography, I just want to put in context that satellites are one of many types of observation that we use in oceanography. But by and large, satellites give us measurements about the ocean surface, mainly surface properties, with a few exceptions, a few important exceptions. But notably, it is mainly measurements of the surface. And so to understand how the ocean works, we need to work with in situ observations. And you see here this sort of diagram that shows the multiplicity of sensors, of gliders, of ships, of buoys, of moorings, of ROVs, etc., that are used to try and understand how the ocean is moving. So satellites just part of it. And the question is, how do we make sense of this diverse network of observations, each with their own space-time kind of sampling and so on? And what is the role for new digital technology? So AI is everywhere. You can hear it. Again, it's in the news almost every day, including environmental research. And a few years ago, 2 years ago, we said, yes, great, it's very interesting, but you can't do better than the weather forecasting system. Now, 2023, apparently AI is actually exceeding or providing better performance than the state-of-the-art high-performance computing. So there's clearly a lot of interest in AI, but we also need to bear in mind that, you cannot predict processes that you do not observe. So NOC has taken a sort of decision for us to invest big time in this digital transformation. This is the sort of typical structure that we have. We have the blue blob is physics. Essentially, the green blob is the biology. Sorry, I'm not a biologist, but marine biology, geochemistry, etc. How is the marine ecosystem responding to climate change? And then we have the two sort of underpinning tools, the modeling and the technology. And what NOC is doing is this sort of investing in digital ocean, led by John Siddle, that some of you will know, which brings together the Earth observations, that is satellites and everything else, with software engineering, data pipelines, all the infrastructure that is needed in order to do digital twins and apply, deploy the power of artificial intelligence. We're building the NOC of the future, and we are developing strategic partnerships in the UK and with the international community. So please, if this is of interest, please come and talk to me. I'm here all day. My summary: there is growing awareness of the critical role of the ocean to mitigate climate change. This is a quote which I leave you to read at length later on, really just to say this is the time where we need to change the way we deal with ocean science. We need a massive pivot towards observing the ocean, which is probably the worst observed system in the Earth system. The ocean observing system is inadequate to monitor the impacts and support local decision making. The satellites provide valuable complement, but there's still important observation gaps, most notably currents, winds, and waves. AI and digital twins provide new opportunities to extract information and value for society. And essentially, NOC has initiated a digital transformation to take advantage of all these different observations and Earth observation capabilities to try and working in partnership with people in the UK and the international community to make this happen. And that's it for me. Thank you.
Thank you very much. I think so much of everything space related is the pretty pictures that we get at the end, and there aren't very many more stunning than those eddies and sediment pictures that you were showing. We are over time. I'll take a question. There we are, Dave.
So I'm just aware that there are a number of missions in the pipeline. Are any of those missions able to fulfill the gaps that you're looking at, or are there more gaps that you need filling?
Of course, there's always gaps. And if SeaStar had been selected, I would not be standing here saying some of these things. I would be giving you a very different take, a very different outlook on what we can do. So no, none of the missions that are in the pipeline are answering these needs that we have identified, particularly in the coastal ocean. It is really what we have at present and for the foreseeable is inadequate to actually look at this. So there are some missions that will give you a few snapshots occasionally, and this is the state we are at now. For example, with Sentinel-1 gives us some snapshots of some of the conditions, but in order to do a systematic mapping, which is what we actually need to do, you're going to need a mission, a dedicated mission to do that. So thank you.
Fabulous.